Well, Yellowstone is one of the country's most visited national parks, but social media rumors about the Yellowstone volcano on the verge of eruption. The ground beneath Yellowstone has begun to shift once more. And this time, the awakening seems to carry a deeper resonance after tremors linked to the memory of Mount St. Helens rippled through the earth. The rising of the land, measured in subtle but undeniable increments, has stirred a wave of attention, as if the vast caldera itself has stretched in its sleep. By early spring, the pattern had become too consistent to ignore. Seismographs began reporting an unusual clustering of tremors, hundreds of them beneath the mountain's northern flank. Most of these earthquakes were small in magnitude, imperceptible to anyone without specialized instruments. Yet their number was extraordinary. Over a span of just a few months, from January into March, more than 400 individual seismic events were recorded, concentrated in the very zone that catastrophically collapsed in 1980. That eruption had been one of the most infamous natural disasters in American history, claiming lives, erasing landscapes, and forever altering the mountain's profile. Now, 4 decades later, something was stirring again in the same scarred region. It wasn't only the tremors. Aerial and satellite imagery began to reveal that the ground itself was changing shape. Subtle swelling appeared in successive measurements, an uplift not obvious to the casual hiker, but impossible for scientists to overlook. This deformation, measured in centimeters yet increasing week by week, often points to magma pushing upward through the crust, displacing rock and soil in its slow ascent. The memory of what happened the last time this bulge appeared still lingers in the minds of volcanologists. In 1980, it preceded an eruption of staggering force. Adding to the unease was the chemical signature emerging from the mountain's vents and fumaroles. Volcanic gas emissions, particularly sulfur dioxide, rose sharply, tripling in concentration within weeks. Alongside it came elevated levels of carbon dioxide and hydrogen sulfide, gases frequently associated with rising magma. When such emissions increase in tandem with both ground deformation and heightened seismic activity, the conclusion is rarely comforting. It usually means pressure is building beneath the volcano, seeking release. Wildlife seemed to sense the shift before humans could fully interpret it. Bird populations that normally filled the air with sound grew noticeably quiet. Elk herds, once a regular sight grazing near the mountain's base, began moving away in larger numbers. Small mammals displayed erratic patterns, appearing disoriented and restless. Animals have long been known to detect minute changes in atmospheric pressure or the Earth's magnetic field. And here, their behavior was speaking volumes. Locals began reporting something else, an uncanny, low-frequency hum, deep, sustained, and seemingly emanating from below. To the human ear, it resembled the faint drone of a distant engine, steady and unsettling. At the Cascades Volcano Observatory, scientists confirmed that this was more than mere folklore. Instruments were detecting harmonic tremors, continuous seismic vibrations often linked to magma movement through underground fractures. While such signs alone might indicate an isolated period of volcanic recharging, this episode was being studied with unusual intensity for another reason: the possibility that Mount St. Helens was not acting in isolation. Geological processes are rarely confined neatly within human-made boundaries, and recent observations elsewhere had sparked a new and troubling conversation. Nearly 900 kilometers, 560 m to the east, under the serene expanse of Wyoming's Yellowstone National Park, another volcanic giant sleeps. Or so it seems on the surface. In recent months, Yellowstone's Norris Geyser Basin had exhibited signs of increased geothermal activity. Steamboat Geyser, the tallest active geyser on Earth, was erupting more frequently than usual in a pattern that some found eerily synchronized with Mount St. Helens' recent restlessness. The idea that two volcanoes separated by hundreds of miles could be connected is not one that scientists raise lightly. Yet seismic arrays beneath Yellowstone Lake had recorded long-period earthquakes, deep, low-frequency quakes often associated with the movement of fluids such as magma or hydrothermal water. GPS monitoring stations detected measurable uplift in the caldera, suggesting a slow, persistent force was pushing upward beneath the crust. This was not the first time the concept of cascading eruptions had been discussed in volcanology. While the public might picture volcanoes as isolated chimneys feeding off separate magma reservoirs, the reality is often more complex. The Earth's crust is a patchwork of plates, faults, and conduits. A significant shift or pressure change in one volcanic system can in theory influence others by altering the stresses in the surrounding crust. Some researchers propose that while direct magma transfer between distant volcanoes is unlikely, the redistribution of tectonic stress could destabilize nearby or even far-flung systems. In the case of Yellowstone, a supervolcano fueled by a deep mantle plume, even small changes in regional tectonic forces could have consequences. If stress patterns shifted as a result of Mount St. and Helens magma movements, they could, in theory, affect Yellowstone's own magmatic system. It was an unsettling but scientifically valid question. Could the rumblings beneath Mount St. Helens be part of a larger chain of events? Adding to the intrigue, satellite-based interferometric radar had detected subtle surface deformations within Yellowstone, changes remarkably similar to those observed before past volcanic episodes. These were not dramatic bulges, but gentle widespread uplifts that hinted at evolving pressure dynamics underground. Historical records showed that such uplift, when combined with an uptick in long-period earthquakes, had sometimes preceded volcanic or hydrothermal events. Meanwhile, advanced computer models began to simulate possible interactions between these two massive volcanic systems using data from seismic readings, GPS deformation patterns, and historical eruption sequences. Some scenarios suggested that even minor disturbances in one system could alter the stability of the other. The probability of a direct triggering event remained small, but the possibility could not be dismissed entirely. As the monitoring continued, the term cascade effect began circulating in both scientific and media discussions. Not just a reference to the Cascade Range, where Mount St. Helens resides, but also to the theoretical domino effect in which one volcanic event could influence another, sometimes across vast distances. This concept was not born from speculation alone. Historical precedents existed. Following Mount Pinatubo's eruption in 1991, several volcanoes in the Philippines and surrounding regions displayed unusual seismic activity. In Iceland, eruptions had been known to alter pressures in neighboring volcanic systems, leading to subsequent activity. Seismic tomography studies revealed deep crust structures connecting parts of the Cascades to regions farther east. While these were not open magma tunnels, they represented ancient fracture-filled pathways that could allow for stress transfer over large distances. In such a scenario, an eruption or significant magmatic intrusion in one volcano could subtly adjust the equilibrium of another. In the eyes of geologists, these developments demanded vigilance. The Pacific Northwest and Yellowstone are both under constant observation. But the convergence of these particular signs, a surge in Mount St. and Helens' seismic and gas activity coinciding with Yellowstone's uplift and geyser changes, was too unusual to ignore. What might be an ordinary recharging cycle for one volcano could, in the wrong combination of circumstances, be a spark in a larger interconnected system. For now, the mountains remain quiet on the surface. Tourists still hike Yellowstone's trails and admire its geothermal wonders. Clouds still drift lazily over the snowy slopes of Mount St. Helens. But beneath both, pressures shift, gases rise, and magma moves unseen. Scientists know that silence in volcanic terms does not always mean safety. Sometimes it is merely the breath before the voice. The science behind the cascade effect is still in its formative stages, but the evidence continues to accumulate. The Earth's crust is not the solid, unyielding barrier many imagine. Instead, it behaves like a complex puzzle of interlocking plates fractured by faults and the devastation it caused locally. Yet, in the years that followed, researchers noticed subtle but intriguing changes in seismic activity at other volcanoes across the Cascades. These shifts did not always lead to eruptions, but they hinted at a level of interconnectedness that had not been fully appreciated at the time. Now, with vastly improved monitoring technology, those hints are becoming clearer. Modern volcano surveillance uses a layered approach. Ground-based seismometers form the first line of detection, capable of picking up even the faintest vibrations from deep beneath the surface. In clusters around both Mount St. Helens and Yellowstone, These instruments detect patterns in frequency and amplitude that help scientists distinguish between ordinary tectonic movement and magma migration. Long-period earthquakes, harmonic tremors, and sudden swarms each tell a different story about what might be happening below. Gas emissions are the second key indicator. Sulfur dioxide, carbon dioxide, and hydrogen sulfide are all common byproducts of magma movement. Specialized sensors, both on the ground and mounted on drones, measure these gases in parts per million, tracking their fluctuations over time. A spike in sulfur dioxide often means that fresh magma has moved into shallower chambers, increasing the likelihood of an eruption. Thermal imaging, both from stationary cameras and satellites, adds another dimension to the monitoring network. This technology detects temperature anomalies on the surface, subtle increases that may indicate new or expanding fissures, lava domes, or heightened geothermal activity. Combined with high-resolution satellite radar, scientists can detect surface deformation with extraordinary precision, sometimes measuring uplift as small as a few millimeters. In the case of Yellowstone, the integration of satellite radar and GPS networks has revealed patterns of uplift and subsidence over decades. These cycles are not unusual in themselves as the vast magma chamber breathes, expanding and contracting over time. What concerns scientists now is the rate of change and its alignment with the unrest at Mount St. Helens. Even if the link between the two is indirect, the synchrony of events is unusual enough to warrant closer scrutiny. Despite the unsettling scenarios such connections imply, the probability of a direct chain reaction between Mount St. Helens and Yellowstone remains low. A much more immediate concern is the potential for either volcano to erupt independently with consequences ranging from local devastation to global disruption. For Mount St. Helens, a moderate eruption could bring lars, fast-moving volcanic mud flows, that would race down river valleys, endangering communities and infrastructure. For Yellowstone, even a small eruption would blanket vast areas with ash, disrupt air travel, and contaminate water supplies. But what if the unimaginable happened? A full-scale Yellowstone supereruption would be unlike any disaster in recorded history. Pyroclastic flows, searing avalanches of gas and rock, would obliterate everything within a 100-mile radius. Cities like Bozeman and Jackson Hole would be reduced to rubble within minutes. The immediate death toll would be staggering, and rescue operations would be nearly impossible in the first weeks. The aftermath would stretch far beyond the continental United States. Ash plumes would rise into the stratosphere, encircling the globe within weeks. Sunlight would dim as a layer of fine particles scattered and absorbed it, dropping average global temperatures by several degrees. This volcanic winter could last for years, devastating agriculture and triggering worldwide food shortages. Ecosystems would collapse as plants failed to photosynthesize, and cascading extinctions could reshape the biosphere. Even lesser scenarios carry severe risks. A smaller Yellowstone eruption could still spew enough ash to shut down major airports, clog machinery, and poison water supplies across multiple states. Transportation networks would grind to a halt. The economic shock in an interconnected global economy would ripple outward almost instantly. Yet, amidst these frightening possibilities, there is reason for measured optimism. Science today is far better equipped to detect the signs of impending eruptions than it was decades ago. The 1980 Mount St. Helens eruption was preceded by clear warnings, bulging slopes, intense quake swarms, but our ability to measure and interpret those signals was more limited then. Now, with 24/7 monitoring, global data sharing, and predictive modeling, the chances of being caught entirely off guard have diminished. Computer simulations allow scientists to explore what-if scenarios, modeling how magma might move in response to changes in pressure or tectonic stress. These models are constantly refined with fresh data, making forecasts more reliable over time. International collaboration ensures that expertise and resources can be mobilized quickly, regardless of where the activity occurs. Public preparedness is also a critical piece of the puzzle. Communities near volcanoes like Mount St. Helens have established evacuation routes and warning systems. In Pierce County, for example, LAR detection networks monitor river valleys for the ground vibrations that indicate a mud flow is on the move. Emergency drills help residents understand what to do when those alarms sound. In regions like Yellowstone, public education focuses on understanding ash hazards and ensuring households have the supplies needed to endure disruptions in transportation and utilities. Ultimately, the unfolding story of Mount St. Helens and Yellowstone is a reminder that our planet is alive, dynamic, and interconnected in ways we are still learning to understand. Every tremor, gas spike, and subtle uplift is part of a conversation the Earth is having with itself, a conversation we are now able to overhear with unprecedented clarity. For scientists, these signs are not merely warnings, but opportunities. Every episode of volcanic unrest, whether it ends in an eruption or fades into dormancy, adds to the body of knowledge that will protect future generations. The challenge lies in translating that knowledge into action before the next eruption comes. Share this knowledge, discuss it, and stay informed. Like, share, and subscribe so you don't miss future updates on the mysteries and marvels of Earth's hidden forces. The next chapter in this story may be closer than we think. And when it arrives, you'll want to be among the first to know.